I'm going to go back into basics here. So this is what we're going to be talking about. I'll move on here. Right. So this is me, if you didn't already know, quite a few fingers in lots of pies globally. And I love my job. I really do love my job. So what we're going to talk about today is I'm going to briefly go on to about data center energy. Of course, cooling can account for that. We'll talk about cooling itself. We'll look at the 53 EU Code of Conduct best practices that I mentioned earlier, and then we'll look at some of the results from our transport industrial cooling and refrigeration ticker project that we're currently working on that's funded by the Department for Energy Security Net Zero, and then I'll open it up for Q&As. So just a brief question. So how much energy is consumed by data centers globally? And the short answer is no one knows. But we know that the International Energy Agency in September 22 said it was between 220 to 320 terawatt hours, or around 0.9 to 1.3% of global final electricity demand. Just want to comment on that 220 to 320. That's a 46% variance. And I'll explain the reason why there is that variance in a few moments. And you can look at that report on that link. And they also published a recent update, which I'll comment on in a few moments. In the EU, our latest forecast is, and this is 5 years old, but they reckon it's going to be up to 92.6 terawatts by next year, and energy consumption is increasing, and perhaps this is something to do with the reason why they've started legislating for data center energy use. In the UK, how much energy was consumed by the UK between the CCA target period 5, between 21 and 23, and we'll talk about that in a moment. So the thing is, all of the data we have is based on a flawed approach, and this leads to poor decision making by both governments, regulators, and I think operators as well. So the Code of Conduct defines a data center as any building, facility, or room which contains servers, server equipment, communication equipment, cooling, and power, and which provides some sort of data service, i.e., everywhere from hyperscale 100 megawatt data centers down to 100 kilowatt data centers, small server rooms located in office buildings. Whereas the climate change agreement for data centers puts the lower limit at 200 kilowatts. And the reason why I think the 46% variance in the IEA report is because they say this in the caveats. So there's no comprehensive data on energy use of all data centers. It's an estimated range based on bottom-up models, ICT sounds figures, available energy use data from large data center operators. And of course, what is the definition of a large data center? So I suspect the IEA is solely looking at the hyperscalers and the large colo companies. And the other thing is that they arrived at this vast range, 46% range, stemming in part from differences in scope, including or excluding crypto mining, the methodologies and the assumptions. So in my mind, it's all a bit smelly. And now we move on to the recent electricity 2024 forecast that was published probably about 6 weeks ago now. And this has been met with howls of outrage from certain quarters, particularly Ireland. And I just don't know what to say. The problem is that when as august a body as the International Energy Agency published these figures, the rest of the press jump on it, and all of a sudden we are now cast even worse than we were before as energy guzzling, fire breathing dragons of data center energies. And that is becoming a bit of a problem in terms of PR for the data center industry. So what they basically said was that energy demand could double by 2026. And they then revised their estimates and it's 460 terawatts, or almost 2% of global electricity demand in 22. It's that doubling that is an issue, because we've discussed it on the previous panel session in some of the questions. There simply isn't the power available to double data center power by 2026. And, I think that maybe somebody at the IEA should have thought about that, but that's just a personal opinion. And this is what they're basically saying. So we're going to see a vast increase in traditional data centers. We're going to get loads of dedicated AI, and crypto mining is going to increase as well. Again, I have to say, I think it's a bit smelly. So I think the problem with data center energy is that globally, we're only reporting the top of the iceberg, when in fact, 85% of data center energy consumption, and from when I say data centers, I'm including server rooms, mobile phone, telco towers, and the communications networks in that. So we're only reporting the top 15%, and we're not looking at the actual iceberg itself, which, as I said earlier, is a problem for policymakers, regulators, and operators. So in terms of cooling, so how much DC energy goes towards cooling? In legacy sites, it could be as high as 50%, or in some cases more. I've personally been to sites with PUEs of 10, which would indicate that 90% of the total energy consumption is being used for infrastructure, including the mechanical cooling. And in some of the new sites, it could be as low as 10% of overall energy consumption. So that would be PUEs of 1.1. There are many examples of sub 1.1 PUEs as well, mostly in the Nordics because they're adopting free cooling. So cooling quick test for everybody. Why do we cool data centers? I'll answer that in a minute. What's the ambient temperature in your data center? What's your humidity window? And why? Right. So these are questions that I ask when I'm delivering my training courses to operators. Let's see what the general answers I get back. Right. So first question, it's usually thermal shock to components, comfort cooling for staff, and to reject the heat. Yeah, okay, I'll go with all of those. What's the ambient temperature in DC? Between 18 to 21 degrees C. Yes, I know that there's data centers out there that are operating at higher temperatures than that, but this is the conventional, the 85% of the enterprise data centers you'll find will still be operating between 18 and 21 degrees. What's your humidity window? And usually it's between 45 to 50% RH, quite a narrow humidity band, and it takes a lot of energy to maintain both 18 to 21 degrees C and also between 45 and 50% RH. And the final question, why? Nobody knows. This is historical. They've been doing it the same way for years, and they don't have access to some of the data center publications. They don't go to the events, so they don't know why they cool it. So I'm now going to give you a brief lesson in cooling. There are two major heat components in a server. The first is the chip, which Jonas was talking about earlier, and they're trying to get the high temperatures on the chip away to you for your more useful services. And the second part is the transformer. So the transformer is actually transforming 220 to 2 volts AC down to the plus and minus DC voltages that are contained on the motherboard. That is a big drop down, and as such, it generates heat. And as you can see from this diagram here, we bring in cold air in the middle, we pass it across the chips and the transformer, and we expel it out the end. And that can be seen quite well in this diagram. So in a conventional air cycle, we have cold air that's coming out of the crack unit into the raised floor. We bring it up through tiles. It's drawn in through the integral fans through the servers, gets heated up, and then the hot air rises, basic physics lesson, and then we direct it back into the top of the crack unit, and then it passes across the coils. The waste heat goes outside and been dealt with somewhere else, and then we've got now cold air, and we push that back under the tiles again. And that's all very well defined. A lot of people sometimes know that, although I have been on sites where I ask them about the air cycle and I get a blank stare. So problem is that we get thermal incapacity, and that's the portion of the cooling system that's in operation but not providing or contributing to the dry bulb temperature change because of return air temperatures, system configuration, or other problems. Bypass air, for instance, and also recirculation air. But both of those problems can be solved by the use of the EU Code of Conduct for Data Center Energy Efficiency And the latest version is the 15th edition, 2024, which was published probably 4 weeks ago and is available on this link. It contains 53 best practices. So just a reminder, if you go onto or download the publication and look through it, there are expected best practices depending on where you are in your cycle. So if there's a green best practice, it's expected to be applied to all. If it's new software, it'll be orange, new IT equipment will be yellow, and if you're doing a new build or retrofit, you're expected to do the best practices that are for the M&E, and the optional ones are in white. So let's quickly go through them. So section 5 contains 7 subsections: airflow management and design, cooling management, temperature and humidity settings, cooling plant, which is split into free cooling and economized cooling depending on the geographic location, and high efficiency cooling plant. We then have computer room air conditioning handlers, direct liquid cooling, and then finally reuse of data center waste heat. So let's look at the first section, airflow management and design. First best practice for new builds and retrofit is design for the hot and cold aisle. Second is design for contained hot and cold aisle. Third is design and contain for hot and cold air retrofit. Then manage that air using cabinet airflow management blanking plates. Cabinet airflow management for other openings in your floor. Provide adequate free air on cabinet doors. Raised floor airflow management, and then raised floor airflow management in terms of instructions. Design return planning. So this would be ducting basically that goes from your hot aisle and directs the hot air straight into the top of the crack unit without hitting into the roof area. Think about your design, raised floor and suspended ceiling height. Think about equipment segregation, and that's for legacy and tight environmental control equipment, where you might need it either to be cooler and have a smaller range of humidity, or a transmission piece of kit which can actually operate at higher temperatures. Your control of supplied air volume, minimizing overpressure. Let me move on to cooling management. So scalable and modular installation and use of cooling equipment, shut down unnecessary cooling equipment, review your cooling before your IT equipment changes, define and review your cooling strategy, define and review your crack settings. An optional best practice is the dynamic control of building cooling. One really important one here, effective regular maintenance of cooling plant, and that will touch upon our ticker stuff in a moment. Review and optimize your chilled water temperatures. Review and, if possible, raise your target IT. So move away from your 18 to 21 and move it up to more 25, 26 perhaps. Review and widen your working humidity range. So instead of being 45 to 55% RH, move to maybe 30, 70. Look at your expanded IT equipment inlet environmentals. Consider separate environmental zones and separate environmental zones for colo managed services. So this is basically moving your transmission equipment to meet the rooms. And in cooling plant, we've got free cooling, economized cooling, and there are a number of solutions: direct air, indirect water with dry cooler and crack, indirect water cooling with crack and integrated free cooling coil, indirect water free cooling with crack and free cooling chiller. And on that point, when we're talking about Schneider Electric, to be honest with you, there is no need for chiller plant in Northern Europe at all. You can probably get away with evaporative cooling and a free cooling coil for the high peak temperatures in the summer. And there's also some more best practices. So indirect water-free cooling with condenser water cooled chilled water, potentially using alternative cooling sources. And you should consider free cooling installations for all retrofit within Europe. And I appreciate that that is easier to do in the north than it is in the south. High efficiency cooling plant. If you are going to use chillers, then choose one with high coefficient of performance. Think about your cooling system operating temperatures. Think about efficient power load operation. variable speed drives for compressors, pumps, and fans. And to be honest, it's almost impossible not to get variable speed drives for air conditioning equipment at the moment. Select systems which facilitate the use of free cooling. Don't share your data center chilled water with comfort cooling. And do not allow non-IT equipment to dictate cooling system set points. And then have a chilled water pump control strategy. For cars and cars, variable speed fans, control on supply, air temperature, not return. Run variable speed cracks in parallel. Sequencing of crack car units. Do not control humidity at crack unit. Cooling size and selection. And then for direct liquid cooling, and this is quite disappointing personally, there's only one best practice. And then for the reuse of data center waste heat, there's waste heat reuse, so kind of formulating that you should be using your waste heat. Then heat pump assisted waste heat reuse, and use your data for waste heat within your system boundary to warm your office, generator, or fuel storage areas. Consider the energy use metrics and reporting, which are now part of the Energy Efficiency Directive. And then think about capture-ready infrastructure. So this is basically to make sure that you extend your cooling loop to the perimeter of your buildings as to be able to connect to an existing or a future district heating network. So just to cover, we've got 12 practices in airflow management and design, 8 in cooling management, 5 in temperature meter settings, cooling plant, 8 in free cooling, 8 in high efficiency cooling plant, 6 for computer handlers, 1 for direct liquid cooling, 5 for data center waste heat. In total, 53 best practices. That's almost a third of the code of conduct. So you can see that it's considered to be quite important. Right, so Ticker project. Very interesting. So the Ticker project is funded by the Department for Energy Security and Net Zero. It's the Transport, Industrial Cooling, Refrigeration Ticker project, and we are leading the data center stream. And you can find out more information about the project on that link. So this is data that was desk research. So in the UK, it is estimated there is 434,000 data centers and offices, including server rooms. And their total electricity consumption is 54.66 terawatt hours per year. Of that, they estimate 13 terawatt hours is down to cooling. Our observations on our surveys, and albeit it was limited, but I cannot believe that this is any different in other server rooms and data centers around the country. We found that the inverters for the chilled water pumps should be able to operate at a much lower frequency to meet the duty. We found poor control of condensing fans, which causes high condensing discharge temperatures and pressures. We found dirty condenser coils. Now, this is a really easy win, right? If your air conditioner is not functioning as it used to, get up there and clean the coil, the external plant. Now, don't clean it from the outside in. You should look at your coil O&M manual and look at how it says, the manufacturer says you should be cleaning it. Invariably, with a V-shaped chiller or coil, you should be moving the fans from the internal part of the V and cleaning against the airflow. And we found that evaporating temperatures are too low for space temperatures. We found a lack of cold and hot aisle containment. We found that the chilled water return temperatures were too low. We didn't find a lot of dry air coolers or non-mechanical cooling. There didn't seem to be any monitoring of operating pressures. We found poor part load efficiency. We found poor performance from hybrid chillers with free cooling circuits. We found the delta T between flow and return temperatures looked lower than expected. We found DX discharge lines insulated outside of the building. And that's another easy win. So if you've got insulated pipe work coming from your internal to the external remove those insulation. They're really not needed. The whole of the cooling plant should be classed as a level 3 secure area. So the only people that should be allowed in it are data center personnel and air conditioning personnel, and they should know how they should operate in that area. We found incorrect pipework drains, leaving the condenser and risers vertically with no receiver or subcooling. This is where basically you're using more energy to get your fluid around the system. And in the service records, we found no operating pressures were available or supplied by the manufacturers or the service company. We found the system lifts were too big. We found no fan speed control for dry air coolers. We found disproportionate pump power. AC motors with forward curved belt dry fans, basically they're always on, so they should be EC fans, which is a code of conduct best practice. And we found short cycling of air for direct and air-cooled condensers. Very little use of adiabatic dry air cooling. That was on our survey sites. There is probably more adiabatic dry air cooling out there in other sites. We didn't find any safe way to clean the condensers or the direct air conditioning. And then we found that the DX liquid line pipework is not insulated in the data hall, so this is actually providing parasitic heat to the data center. So yeah, insulate them inside the halls and take off the insulation outside the halls. So this is who we're working for on that project. Ourselves, Carbon Trust, Carbon Technologies, Institute for Refrigeration, Star Technical Solutions, University of Birmingham and London South Bank. So moving on to legislation, and although this is primarily EU legislation, as part of our TICA project, we have to provide recommendations to DNES, and so there is a distinct possibility that the legislation will hop over the channel. So here we have data centers. Currently, they're getting, in order to obtain green finance, you'll need to, if requested, do an assessment under the Taxonomy Climate Delegated Act to the assessment frameworks available on the EU Code of Conduct website for the investment partners. So that's downward pressure on the data center. We also have Corporate Sustainability Reporting Directive, and in the UK that would probably be this streamlined energy and carbon reporting. But this is basically an organisation that's using co-location or cloud services will be wanting to find out their GHG Scope 3 emissions, and they'll need to look at their data centres for that. So that's up pressure from our customers. And we've got the Energy Efficiency Directive, which I'll go into in a little bit more detail in a moment. And that is direct reporting of metrics back to the Commission. And that's the next more downward pressure. The Corporate Sustainability Due Diligence Directive is allied with the Corporate Sustainability Reporting Directive. I'm not too worried about it at the moment, but that deals with things like modern slavery, which will have an impact on the IT supply chain. We've got the Digital Operations Resilience Act, which is basically third-party audits of financial services companies, which could be in co-location sites as well. And then we also have the Taxonomy Climate Delegated Act from 2025, and I'll talk about that in more detail in a moment. And then we've got the climate transition plans that data centers will need to be publishing to their stakeholders and basically to their commission as well. And I think that leads back into the session that we had with Schneider. What are you going to do about retrofitting your legacy cooling systems moving forward? This is all wrapped up in the climate transition plans. There's a number of EU standards that I would advise everybody to look at. EN 56-1, general concepts, -2-1, building construction, 2-2, building power supply and distribution, 2-3, environmental control, 2-4, telecoms, 2-5, security. Not that it applies to UK, but most certainly in places like Iceland, earthquake and seismic risk. And then the 3-1, management and operational information. And they're also contained in the ISO IEC Treble 237 series. We also have the data center KPIs, and these are the ones that are asked for by the Commission. So we've got PUE, renewable energy factor, IT energy efficiency, IT equipment utilization, energy reuse effectiveness, heating efficiency ratio, carbon usage effectiveness, and water usage effectiveness. Now, of those, there's only 3 that you need to worry about for compliance reporting: that renewable energy factor, your energy reuse effectiveness, and your water usage effectiveness. Now, there is also one that if you haven't got a copy of, I would advise everybody to go out and purchase one. It's available on our website. 5-1 maturity model. This includes the best practices that were originally called TR99-1, practice for energy efficiency, which is basically the standardized version of the code of conduct. You can buy the code of conduct, but you can get the code of conduct free. And also the practices for sustainability. Those have both been withdrawn because most of the best practices have now been incorporated into the 5-1 standard maturity model. There is also the 99-3, which is the guidance to the application of the 5600 series. So the taxonomy is in force. The Corporate Sustainability Reporting Directive is in force, and the Energy Efficiency Directive is now in force, as of yesterday, I believe. Most of them link back to the Code of Conduct for Data Center Energy Efficiency in some way, shape, or form. The reporting requirements are based on the EN 5600 series, and the taxonomy is very much likely to be an assessment to the 5600 5-1 standard from 2025. I say highly likely. That is down to DG FISMA as to how they approach that. So what does the Energy Efficiency Directive apply to? So it's for data centers over 500 kilowatts of load. You will need to provide your total energy consumption, a percentage of that consumption or supply derived from renewable energy, and you will need to provide your water use. There is also some energy administration stuff there, which is very similar to the application process for the EU Code of Conduct. You will have to provide to report how much, if any, waste energy is being reused outside the system boundary. It was supposed to be reported by the 15th of May in a couple of weeks' time. Because the EU haven't got their registration portal set up, it's been pushed back to September. So you will need to report your 2023 data by September 24, and then your 2024 data by May 25. So this is what the maturity model looked like. It's spread into 8 pillars: management pillar, infrastructure buildings, power supply and distribution, environmental control, and then ICT software, compute, storage, and network. This would be for this slide diagram would be for a enterprise customer, and this one would be used for a co-location, where obviously the co-location operator has no visibility of what IT the customer is putting in to their cages or racks. In this case, it's a house network system, so they have included there. And there are 5 levels of maturity, and the best practices will give you some guidance on that. Okay, so just to cover, this is the legislation.